Hello there, and welcome back. In this video, we're going to continue our discussion of comparing different parameters for different populations. In the past videos, we've compared the proportions between two populations and the variances between two populations. In this video, we're going to be comparing the means between two populations, and there's going to be three different variations of what we call the t-test for the equality of means that we will be discussing. So let's begin by stating the general framework for which we're going to be working in. So let's assume we have a population A. This time we're going to be looking at the mean of A, which I'm going to be represented by mu A. We're going to be going into this population and gathering a simple random sample. I'm going to call it SA, and there has to be a point estimate associated to the sample that we're going to use for mu A, and we already know that that's going to be equal to x bar A. And similarly, there's going to be another population B with some mean. I'm going to call it mu B. We're going to be going into this population, gathering a simple random sample of size, let's call it NB, and there has to be a point estimate for mu B, and that's of course going to be equal to x bar B. The null hypothesis that we're going to be working with today is going to be equal to the claim that mu A and mu B are precisely equal to the same, with the two-sided alternative that mu A and mu B are significantly different from one another. Now, let us assume, for the sake of discussion, that both of these populations are normally distributed. So both normally distributed. And if not, we can use the central limit theorem to talk about the distribution of the sample means, or the differences between sample means, for which we have discussed with the single population discussion. So keep these things in mind. We are assuming that these populations are normally distributed, and if not, we're assuming that the samples we're drawing from them are large enough for which we can employ the central limit theorem to describe the distributions of sample means. So we're going to be going about testing this two-parameter hypothesis with the same exact approach that we did for the proportions. So what we're going to do is we're going to be defining the differences of means, mu d, to be equal to mu a minus mu b. And of course, if you define it as the other direction, you're just going to get opposite results but equivalent conclusions as long as you're working with the two-sided alternative. So what would be a point estimate for mu d? You may already want to guess what that is, but that's going to be x bar d, where x bar d is going to be defined to be equal to x bar a minus x bar b. Make sure if you are defining these things that these are in the same exact direction. You cannot mix them up. So the first question that we need to answer is x bar d an unbiased estimator for mu d? And we should already know how to assess that. So the expected value of the random variable, x bar d, is of course going to be equal to the expected value of its definition. So it's going to be x bar a minus x bar b. Keep in mind these are not numbers, they are random variables. So technically these should be capital X and capital X sub b. So by properties of expected values, I can distribute that over the difference, and that's going to be equal to the expected value of x bar a minus the expected value of x bar b. So we already know that x bar is an unbiased estimator for mu, therefore this is going to be equal to mu a minus mu b, which is of course the definition of mu d. Therefore we have that the expected value of the random variable for the sample mean difference is equal to the population mean difference, therefore x bar d is an unbiased estimator for mu d, so that is wonderful. Now we need to figure out what the standard error associated to this estimate is for this particular parameter, mu d. So we of course begin the same exact way by finding the variance of this. So that's going to be equal to the variance of x bar a minus x bar b. And let's assume that these two are independent samples. If they're independent, we can ignore the covariance term and distribute this variance over this difference. That's going to give us the variance of x bar a. Keep in mind that's going to change to a plus, variance of x bar b. We already know formulas for the variance of sample means. That's just going to be equal to sigma a squared divided by n a plus sigma b squared divided by n b. So that is the variance of the difference. Therefore, the standard error associated to using x bar d as a point estimate for mu d is just going to be equal to the square root of sigma a squared over na plus sigma b squared over nb. And that gives us our standard error formula. As you should already know, even though this is the theoretical form of the standard error, we can only use if sigma a squared and sigma b squared are both known. If they are both known, then we can be using a z critical value associated to our distribution of confidence, but if you only know one of them or neither of them, you should be using a t distribution. So, if this is the case, and let's assume that sigma a squared and sigma b squared are both known, how would we construct our confidence interval? So if these things are known, then the margin of error is going to be equal to the z critical value times the standard error associated to the estimate for x bar d, and therefore the confidence interval under some level of confidence for the differences between means is going to be equal to the point estimate minus our margin of error, and then the point estimate plus our margin of error, and that gives birth to our confidence interval for the differences of means. So keep in mind the null hypothesis is that the difference between them is equal to 0 or practically equal to 0. Therefore, the only number that we really care about here is going to be 0. So if 0 does belong to this confidence interval, then we're going to be failing to reject the null hypothesis because that means our point estimates are really close to each other in terms of the individual sample means. Therefore, we have evidence to believe that they are, the mu a and mu b, are proximally equal to one another. And if 0 is not inside of the confidence interval or the interior of these boundaries, then we're going to be rejecting the null hypothesis, because that implies that one sample mean is significantly greater than the other, implying that the population mean of one is significantly greater than the other population mean. So that is the framework for hypothesis testing for the differences of means. Now let us take a look at these three cases that we're going to be discussing in the rest of this discussion. So case 1 begins by assuming that the populations A and populations B are dependent populations. So this case is actually going to be referred to as the paired difference t-test. So the paired difference t-test. So there is some connection between these two populations. The most common example that is associated to paired difference t-test probably would be the before and after studies. So let's assume that we want to study the average happiness of individuals. And let's assume that this number for happiness is any real number, so negative infinity to positive infinity, that it can be equal to each other. So if this is the case, then how are we going to go about studying this? Well, we need some other variable in presence of happiness, right? So for example, are people more happy after they eat or before they eat, or maybe after they exercise or before they exercise? So let's just take an example. Let's do exercise. So let's do 5 individuals. 5 individuals before and after they exercise. And let's analyze their happiness before and after they exercise. So let's assume before they exercise, so this is going to be population A. So the first person, let's assume, has a happiness level of 47. Second person has a happiness level of 38. The next one has a happiness level of 53. Let's do 21. And let's do 42 for the second. So population B, so this is going to be after they exercise. So let's look at their happiness and see what happened to them. So 1, 2, 3, 4, and 5. So in terms of what we mean by dependent populations, that means these two values are associated to each other, those two, those two, those two, and those two. So if, for example, you sample somebody before and they don't show up for after, you should be disregarding their values if you're doing a before and after study. There should be a pairing between them, or a one-to-one correspondence between them. So let's actually write that. So 1 to 1 correspondence. Cool. So for person 1, let's assume after they exercise, their happiness increases to 55. Let's do 44, 50, so that means person 3 decreased in happiness after they exercise. So maybe something happened, maybe they hurt themselves, twisted their ankle or something like that. But let's assume everybody else does decrease. So let's look at the average happiness between them. So the average happiness of before exercise was equal to 40.2, and the average exercise of B, this is going to be equal to 45. So one can then ask, is there a significant difference between these two averages? If there is, then we can pretty much say that, oh, generally speaking, when people exercise, then people are usually happier after they exercise versus before they exercise. So what we're going to do for the pair difference t-test is we're actually going to create a new population. This is going to be called the population D, and this is going to pretty much reminisce of the parameter mu D, which is going to be equal to, I'm going to define it to be mu B minus mu A, because most of the values in B are greater than in A, so I want my averages and my average differences to be a positive number. That's just personal preference. So let's look at 1, 2, 3, 4, and 5 again. So we're going to be subtracting these two. So 55 minus 47, that's going to be equal to 8. 44 minus 38, that's going to be equal to 6. And then we're going to have minus 3, 11, and 2. So practically most everyone's happiness did increase by at least 2, with the exception of person 3. So maybe 3 is an outlier, but let's not go into the outlier discussion here. So what you can then do is calculate the mean difference, which can come out to 4.8. And we're also going to be needing the standard deviation of these differences. All right, so the standard deviation of these differences. And that's going to be equal to 5.4498 approximately. All right, so these two things are going to be what we need. Now keep in mind, if you do define this difference to be backwards, so mu A minus mu B, this point estimate is going to be negative, but this is going to be the same, regardless of the direction for which you subtract, which is a nice little analytical proof in case you're not already aware of this, but that is indeed true. So now what we're going to do is we're going to look at the standard error associated to using x bar d as an approximation for mu d. Right, so remember, SE x bar d is going to be equal to, so technically if we just replace, so let's just ignore this x bar d for a moment, let's just call it x bar. Remember, this is just going to be equal to sigma divided by the square root of m. So if we sort of replace x bar with x bar d and sigma with sigma d, then we get this particular form. So what is sigma d? So sigma d is the standard deviation of all differences of population B minus population A. So I guess that's the happiness of B minus the happiness of A, right? So that's the standard deviation of all of those things. But keep in mind, you technically do not know these values. So this sigma sub D doesn't really have any value. So what we can do is we can approximate this parameter, sigma sub D, with this point estimate, S sub D. So that's where our T distribution comes into play. So this is approximately equal to S sub D over the square root of n, and one can find that that's going to be, of course, equal to approximately 5.4498 divided by the square root of our sample size, which is 5, and that's going to come out to approximately 2.4372. Please keep in mind that this is the number of pairs we have. So it's not equal to 10 because we have 10 numbers in the original sample. It's the number of pairs that we're studying, or the number of individuals or people who participated in our study. All right, so now that we have the standard error associated to our estimate, we should be able to calculate our margin of error for our confidence interval. So how are we going to go about doing that? So let's assume alpha is going to be equal to 9%, forcing our level of confidence to be 91%. Since we're not using the parameters, we're using the statistics for our samples, that means we will be using a t-distribution to model our level of confidence. We're working with a two-sided alternative. That means this area should be 91%, with the tails equally weighted. So one can find, let's see, so keep in mind n is equal to 5. That means the degrees of freedom is going to be equal to 4. That means this distribution is a T4 distribution. So this two-sided t-critical value can be found to be approximately equal to 2.2261. Once you have your t-critical value, and keep in mind the degrees of freedom is equal to the number of pairs minus 1. Keep that in mind because the other two methods of testing the differences of means are going to have a little bit different degrees of freedom. So once we have that, then we can calculate our margin of error. So that's going to be equal to the t critical value times the standard error associated to the estimate, x bar d for mu d. This is going to stay consistent for all of our confidence intervals, which is actually pretty nice. That's going to come out to 4.4255. All right. So if that's the case, let's construct our confidence interval. So remember the confidence interval for the differences between means under some level of confidence C, and we've chosen 91%, so we can just write that there just for clarity. Keep in mind this is just going to be equal to x bar d minus epsilon and x bar d plus epsilon, and that's going to be equal to negative 0.63 up to 10.23. Keep in mind that the null hypothesis is that the difference is null, so we just need to compare the number 0. See, the left boundary is negative and the right boundary is positive. That means 0 is in between them. Therefore, since 0 does belong to our confidence interval, then we fail to reject, barely, the null hypothesis that the differences between them, or we can just go to the original, mu a is equal to mu b. And the reason I say barely is because if we look at this graphically, so if 0 is here, there's our left boundary, so x bar d minus epsilon and x bar d plus epsilon. The majority of this interval is lying on the right-hand side of 0 with a very small interval to the left of it. So that's why I say barely. This is, weak evidence, some people would say, but nonetheless, it is not good enough to reject the null hypothesis. But it's almost, if we were to change a couple other things, maybe we would reject, but based upon these statistics, we would fail to reject the null hypothesis. Now let us lay down the theory for cases 2 and cases 3 for the differences between population means. So for case 1, we assume that the populations were dependent, but for case 2 and case 3, we're going to assume, so both assume that PA and PB, the populations, are independent. That means the samples we draw from them should also be independent. So the guiding question in terms of which case do we use here is going to be the following one. So does sigma a squared equal to sigma b squared? Or equivalently, because sometimes we don't know the variances, or sometimes we do not know that they are equal, or do we have evidence to believe? That they are. Some people will call these populations homoscedastic, just meaning that the variances between them are equal to each other. So do we have evidence to believe that they are? So what test talks about the equality of variances for two different independent populations? Keep in mind that is going to be the F-test. So the F-test for the equality of variances definitely can come up here as a predecessor to case 2 and or case 3. So if the answer is yes, the population's variances are equal to each other, or we have evidence to believe that they are, then we will be using case 2, which is called the pooled variance. Pooled variance t-test. And if the answer is no, then we're going to be using case 3. You can take a guess what this is called. It's going to be called the unpooled variance t-test. The unpooled variance t-test is actually the easier of the two to use in terms of calculations. The only complication with case 3 is the calculations of the degrees of freedom, which we'll definitely get to. So let's briefly talk about the theory associated to case 2 for the pooled variance t-test. All right. So the pooled variance is going to be equal to the degrees of freedom for A times SA squared plus the degrees of freedom for B times SB squared, the variance of B, all divided by nu A plus nu B. If you remember from the discussion for the pooled proportions test for comparing two proportions of two different populations, the pooled proportion had a similar structure to this. So what we're doing is we're pretty much weighing the variances with respect to their sample size. So it's practically the same exact thing. Also, keep in mind, this bottom is actually called the degrees of freedom for the test, actually. So the degrees of freedom that we're going to be using for our t critical value is actually just going to be equal to nu a plus nu b, which is actually just the same as the sample size of a plus the sample size of b minus 2. All right, so we're working with two different independent samples. So pretty much the degrees of freedom is the total sample size minus 2, which is just minus 1 minus 1. So what are we actually doing here when we're pulling the variances together? So we're sort of combining or creating one sample of size NA plus NB. We're pretty much bringing them together into the same one because pretty much we can, because they have the same exact variances, and we're pretty much testing to see if the means are equal to each other. So yes, we're creating one sample and we're sort of deciding, is that appropriate or not. So if this is the case, because we're assuming that the variances between them are equal to each other, because that's the assumption of this whole entire pooled variance t-test, let's actually just call these variances one number. Let's call it sigma squared. So if that is the case, what is the standard error associated to using x bar d as the estimate for mu d? So remember, that's generally speaking equal to sigma a squared over na plus sigma b squared all over nb. So if sigma a squared and sigma b squared are equal to the same exact thing, then we're just going to have the square root of sigma squared over na plus sigma squared over mb. We can factor out sigma squared out of the radical, and that's just going to give us sigma times the square root of 1 over na plus 1 over nb. Has a very similar structure to the pooled proportion z-test for the differences in proportions. So now we have this question, so we need an approximation for that. So we need an approximation for this common variance, or this common standard deviation rather, right? Because if the variances between the populations are equal, that means the standard deviations between them are equal. So what we can do with this pooled variance is we can use the pooled variance to approximate the variance, and also the pooled standard deviation to approximate the standard deviation. So we can approximate sigma with the pooled standard deviation, because you can't use the standard deviation of one of them, you can't use the standard deviation of the other one. You need to sort of use a weighted standard deviation between both of them. That's where the pooled variance sort of comes into play. And keep in mind, the pooled standard deviation is just the square root of the pooled variance. So once we have that, that means the standard error associated to using x bar d is now going to be approximately equal to the pooled standard deviation times the square root of the sum of the reciprocals of the sample sizes of the samples that you drew from the populations. So once we have that, now we can go ahead and construct our margin of error. So our margin of error is going to be equal to the t critical value times the standard error of the estimate x bar d for mu d. And keep in mind, for this t critical value, the degrees of freedom that we're going to be using is going to be equal to na plus nb minus 2. All right? So once we have the margin of error, that means the confidence interval for the differences of means under this level of confidence under the pooled variance approach has the same exact structure as before, x bar d minus epsilon and x bar d plus epsilon, and the conclusions for this will be the same. Now let us look at case 3. So for the unpooled variance t-test, which is case 3 of these methods for testing the equality of variances, means, this one is going to be safe to use if one of these 3 cases apply. The first, you aren't sure if the variances between the populations are equal. Second, you have evidence to believe that the variances are not equal to each other. So that's of course the F-test in disguise. Or you know directly that the variances between them are not equal to each other. This last one, of course, is the most unrealistic one, because typically you would have to know the variances of them, or you would have to know that the differences between the variances are exactly 0, or approximately close to it. So, if this is the case, the only difference between this and the standard error is that the standard error, keep in mind, for x bar d was exactly equal to sigma a squared over the size of a all over sigma b squared over the size of sample b. Since we cannot pool our variances of our samples together, we have to treat them individually because we do not necessarily know who is actually the larger or the most influential variance of the two populations. So we have to treat them different. So we're just going to treat sigma a squared with an approximation, so the variance of A, sample A, and we're just going to approximate the population variance of B with the sample variance of B. So this is just going to be equal to approximately SA squared over NA plus SB squared over NB. So that's of course the most trivial looking standard error of the estimate for x bar d, and of course it's the most commonly used one, I guess you could say, because we usually don't know anything about the population variance. Therefore, the margin of error is going to be equal to the t critical value times this standard error of the estimate for x bar d. Now, here comes the downside of the last one. What are we going to use for the degrees of freedom? Are you going to use the first one, the second one, a weighted average? Yes, the weighted average of these degrees of freedoms. But what would an appropriate weighted degrees of freedom formula look like? So this approximation, which is sometimes referred to as the Welch Satterthwaite, or just the WS approximation for the degrees of freedom, for this, some people call the unpooled variance t-test also the Welch t-test. It's another common name for it. But the Welch approximation, or the Welch Satterthwaite approximation for V, is going to be equal to the variance of A divided by the sample size of A plus the variance of B all over the sample size of B, the quantity squared, all over the variance squared, which is the same as the standard deviation to the power of 4, all divided by the sample size of A squared, degrees of freedom for A, and then the variance of B squared, which is the same as the standard deviation of B to the power of 4, all over NA squared, degrees of freedom for A. I'm not going to go through the proof of this, but generally speaking, this is resulting from a quotient or a balance of chi-squared random variables, generally speaking. But you can sort of think about this. Oh, also before we get into a brief analysis of it, this top thing inside the bracket should look vaguely familiar to you. That's the inside of the square root of the standard error of the estimate for x bar d, right? So remember, SC x bar d is going to be equal to SA squared all over NA plus SB squared all over NB, right? So if we don't write the square on it, we're just going to get that. So if we square both sides of that, we get the top of this degrees of freedom thing. So technically, that's just the standard error to the power of 4. So we can actually just write that here. So that means V is just equal to the standard error for the unpooled variance t-test to the power of 4 all over that bottom term. Standard deviation 4, sample size squared, nu A, plus standard deviation 4, sample size squared, nu B. Right? So this is our degrees of freedom formula. If you're working with t-tables or something, of course you would have to round to the nearest integer, but if you're working in Excel or Desmos, you do not need to round this to the nearest integer. So that's great. So once you have this degrees of freedom, then we of course have our t critical value calculated under some level of confidence times the standard of the estimate associated to x bar d. And again, the confidence interval for the differences of means under some chosen level of confidence is again going to be x bar d minus epsilon and x bar d plus epsilon. And again, the same interpretations apply. Now let us go through an extensive example on how we would determine which test to use and go through the process of calculating all of these things for a t-test for the differences between two population means. So let's assume we're interested in determining if there is a significant difference between the systolic blood pressures between two populations A and B. Let's assume we're working under this alpha level. So what we're going to do is grab a sample from A, and let's assume we grab 37 people, measure their blood pressures and take the average. Let's assume we get 123 millimeters of mercury with a standard deviation of 326. In the second population, we're going to grab 28 people, take their blood pressures, take the average. We get an average of 134 with a standard deviation of 7.62. So the question becomes, are these two significantly different enough in order to imply that the means between them are unequal? So the main null hypothesis that we're trying to test is that mu A is equal to mu B. So is this claim true? So we're going to be defining the differences between means in this fashion. Let's just do mu b minus mu a, because we clearly see that x bar b is bigger than x bar a, and I prefer to work with positive numbers. Now you may think, well, obviously the average of b is larger than the average of a, but is that difference due to the variation in these populations? That's usually why we have to understand if the variances between them is equal to the same exact thing. Because if the variances between them are equal to the same thing, then we have more evidence to believe that these averages are significantly different. But if the variance of B is significantly larger than that of A, that might be contributing to this particular average. Keep in mind the sample size might be subjectively small, leading to that larger average, and hence the difference between them. So that's why we need to analyze the variances when we're talking about the differences between means here. So if we use a point estimate of x bar d, which is of course going to be equal to x bar b minus x bar a, we should get a difference of 11 millimeters of mercury. So we need to figure out, is that number significantly close to 0? So before we go into a differences of means, we need to answer the question, are sigma a squared and sigma b squared equal to each other? Well, it's not given in the problem statement that they are, so we need to conduct an F-test on the claim that the variance of A and the variance of B are equal to each other. So this is a baby or subset hypothesis test. So let's go with a two-sided alternative that sigma A squared is not equal to sigma B squared. So how are we going to test the equality of variances? So we already know that the easiest way to do that is to study the quotient of the variances and compare the quotient to 1, right? So again, we're going to be using a two-sided level of confidence here. And also keep in mind the level of confidence does not need to be the same for the F-test and the associated t-test that we're using. So they can be different. They need not be the same. So what is sigma q squared? So let's quickly review that. So sigma q squared, let's define that to be equal to sigma a squared over sigma b squared. And again, it doesn't really matter which one you use because we have a two-sided critical value to compare. So that means the point estimate for sigma q squared, which would be sq squared, is just going to be the variance of A divided by the variance of sample B. And you can find that's approximately equal to 0.1830. So this is our F test statistic. So what are we going to compare this to? We're going to compare that to the critical values. So this is our F distribution. So we need to make sure we get our degrees of freedom right. So our numerator is associated to A. So that's going to be associated to this particular sample, and B is associated to that particular sample. So the top has a degrees of freedom of 36, and the bottom has a degrees of freedom of 27. So make sure you get those in the right order. So this is an F3627 distribution. We're working with a two-sided level of confidence here. So this is going to be, of course, equal to 1 minus our alpha value of 0.62, which is going to be equal to 93.8 if you want to write that. So this is going to be our left critical value, our right critical value. So we're probably going to be comparing it to the left one since we have a number that is less than 1. So one can find that these critical values, FL and FR, that's not an F, so FR is approximately equal to 0.51 and 2.02, right? So we're going to compare our test statistic for F to these, and we clearly see that our test statistic is to the left of the lower one. So therefore, since our test statistic is less than the left critical value, or keep in mind f stat is greater than the right critical value, would also be an equivalent conclusion, then we reject the null hypothesis claim that the variances between them are equal to each other, right? So what does that mean? So that means we have evidence to believe that the variances are not equal to each other. So if the variances are not equal to each other, and we want to conduct the hypothesis test that mu A equals mu B with the two-sided alternative that mu A does not equal to mu B, which test are we going to be using? So clearly we do not have a dependency or one-to-one correspondence between them, so the pair difference t-test is not appropriate here. And in terms of the pooled versus unpooled variance t-test, we can only pool if we have evidence to believe that the variations amongst these populations are the same. Therefore, since we have evidence to believe that they are not, we will be using an unpooled variance t-test here, or the Welch's t-test, in order to conduct this hypothesis test. So if that is the case, we just need to calculate our standard error of the estimate. So the standard error of the estimate for x bar d is going to be equal to the square root of the variance of sample A over the sample size of A, the variances of sample B all over the sample size of B, and you can find that that's approximately equal to 1.5365. Now we're going to calculate our degrees of freedom for the unpooled variance t-test. Remember, the degrees of freedom is approximately equal to the standard error of the estimate for x bar d all to the power of 4, all divided by the variance squared, which is the same as the standard deviation to the power of 4. So let's just write that clearly. All divided by the sample size of A squared, nu of A, plus the sample standard deviation to the power of 4, all over sample size of B squared, degrees of freedom for B. Once you actually work that out, you find the degrees of freedom for this is approximately equal to 34.5011. Now, if you're working on an t-table, you're probably going to round that to either 35 or 34, or possibly even take the average of the associated t-scores for that. But if we're just working in the analytical realm, you can find that the t critical value under this particular degrees of freedom, under the stated level of confidence, is going to be approximately equal to 1.9299. Once we have our t critical value, so all the hard parts is done, so the margin of error is going to be equal to the t critical value times the standard error of the estimate of x bar d, and that's going to come out to approximately 2.97. And that, keep in mind, that's in millimeters of mercury, or the difference in blood pressures, right? So that means our confidence interval for the population mean difference in systolic blood pressures between these two populations under a 93.8 level of confidence is going to be equal to 8.03 and 13.97. And keep in mind, this is in millimeters of mercury. So keep in mind, the null hypothesis was that mu d is equal to 0, i.e. there is no significant difference between them, so therefore we only need to compare 0 to this interval. Since 0 does not belong to that interval, therefore we have evidence to believe that there is a significant difference that mu d or mu a does not equal to mu b, right? So we reject this claim. So some people will say we accept that mu a does not equal to mu b, or somebody may even say that mu b is significantly greater than mu a or something like that. But of course that conclusion is optional. So those are the three main categories of testing the differences between two population means: the pair difference t-test, the pooled variance t-test, and the unpooled variance t-test, where we use the f-test in order to determine whether there was a significant difference in the variances between these populations to determine whether we can use pooled versus unpooled variances. I hope you enjoyed this video, and I'll see you in the next one. Take care.